Okay, so we're going to talk about watermarking, and we're going to run this as the State of the Union. I don't know whether you've seen the US State of the Union. So if you don't agree with something and you groan, make faces, clap, stand up, and jeer at me, please do that. Because I think I just want to kind of, make this more into a discussion. So I attended this excellent talk by Matt Turak, who ran this DARPA program called Semaphore, which was about deepfake detection. And thanks, Matt, for his slides. We think of fake media as something new, right? We just saw the whole Taylor Swift incident. Actually, it goes back quite a bit. So I will have to take my notes. Okay, I was like had to look up some of this stuff on the internet. So anybody know what that picture is? So there was a portrait, that one portrait of Abraham Lincoln. It's actually, the body is not Abraham Lincoln's. It's actually somebody called Calhoun, whose body one of the photographers really liked. So they put the body of Calhoun and that the faces of Abraham Lincoln. Okay, they thought it worked better. And apparently it was very common touching up these pictures. Okay. What about this? Anybody know this? I had to look up. I took notes. Uh, that is Ulysses S. Grant. That picture is very famous, but apparently it is all fabricated from those three pictures. Okay. Uh, so that's 1902. So all I'm saying is, like, this is not a new phenomenon. This is a picture of something called Cottingley fairies. And, this shows one of the cousins, Francis Griffith, dancing, with the fairies. And actually, Arthur Conan Doyle used this quite a bit to sort of motivate him for the novels. Okay, this one is on the left. It's Yezhov. He was the head of police for Stalin, but then Stalin got mad and he was also executed. And that's what happened to him in the picture there. Okay, so the whole idea here is that it is not, fake media is not new. It was there before. Apparently, there are a lot of tampered pictures. But you can imagine, right? So the cost of doing this, right? Either you draw a whole new painting, or you actually have to go to the, take those negatives to those rooms and, cut and so on. So the whole idea is that the phenomenon is not new. And obviously then, the GANs came, and now it's text to image. So it's just much easier now to do that, but the phenomenon is not new. Okay. So, you can do text to image generation, text guided image editing, and all that, and so on and so forth. And I'm not going to go too much into that. Here are some examples that I really like on fake media. By the way, we could do probably a whole lecture on just fake images. It's being used quite a bit in elections in India. So, for example, this candidate actually, he grew up in apparently London or someplace like that, didn't know the local language. By the way, there are like 23 plus local languages in India. And he basically made a deep fake of him speaking in the local language. And so I don't know whether you call it deep fake or he's, just trying to get his message. There was this picture that came out like maybe last week or maybe a couple of weeks back, which later people found out to be fake. So it's being used in election quite a bit. And you can just keep going, right? There was this image of Pentagon burning, which turned out to be fake. Some fake, fake pictures about Elon. Then there was a fake photo of Selena Gomez that went viral. By the way, there is some legit use of deepfake as well. This is one of the biggest movie stars in India, Shah Rukh Khan. And what they did is they made an ad in Hindi or Urdu and then actually dubbed it in different languages in India. So I guess this is So, there are legit uses as well. So deepfake is here, and people have started, I think governments have started reacting to it. Um, so there is Gen AI laws sort of passed everywhere. EU, NIST, USA had a Biden executive order. Um, China. By the way, one thing I was very surprised, I just attended something at Georgetown. The China's AI law is quite extensive, much more than others, which was very surprising to me, actually. India just enacted one, and more are coming. And essentially, all these laws mention, most of them will mention watermarking. Sometimes they don't call it watermarking, but it's basically, they refer to watermarking. And essentially, all they say about watermarking is, thou shalt watermark. That's it. So that's kind of from the executive order for Biden's executive order. And notice that there is no nuance here that what is it good for? It's like saying, thou shalt encrypt. I don't care if you use a broken scheme. Okay? This is from my birth country. I'm now a US citizen, but grew up and was born and grew up in India, which basically, essentially, the prime minister is saying that, yeah, we need to figure this out. That's it. There's no nuance here about what these are good for, what they are not good for. So essentially, what all these they are looking for is essentially an LLM Turing test, which says in world 0, you're giving a text that comes out of natural distribution. World 1, I give you something that came out of LLM. Go and distinguish between those two worlds. And there is a lag between when I press and coming over here. So sorry about that. So the first set of detectors were all basically relying on this fact. I don't know whether you've heard of Detect GPT, and all they're basically relying on is that the distribution of the text generated by the model is different from the natural distribution. Okay. Now, if you, like Dan Klein from Berkeley has some excellent work on that just recently. Now, if you think that works, then you won't need watermark. Okay, we can stop now. We can take an early break. But the problem is that they're very easy to bypass. They get their NeurIPS paper, and the next conference somebody breaks it, gets an ICML paper, then they submit something to ICLR, and the next conference somebody else breaks it. And I think there's a fundamental tension here, right? It's like basically saying that the LLM's goal is to get close to the natural distribution as possible, and they're relying on the fact that these distributions are different. Okay, we'll talk a little bit about that as well. Now, watermarking does something different. It actually will embed a signal so that it will force the distribution slightly to be different. Okay? Okay. So the idea is, by the way, I am not trying to be exhaustive here. A lot of my discussion is based on some of my work and some of the early work by Kirschenbauer that came out of Jonathan Katz, and there since then a lot more watermarking schemes. Okay, I'm just trying to make a point here. So the idea is to embed a watermark in a machine-generated text, and then when you try to detect the presence, you want to talk about two things. False positive, that text generated without the knowledge of watermarking is labeled as watermarking, is watermarked. False negative is text that you actually watermark is not generated, detected as such, right? So you can talk about both those things. And generally, at least in this literature, people have, so detection should be easy, and you should not need the model parameters for detection. Now you can sort of debate that, but I'm going to take that as one of the requirements and go ahead with that. There are schemes that actually require those models as well. And since we don't have, we are poor academics here. I don't know how many are academics. We don't have all the GPUs, so we don't want to retrain the model. Okay, so I'm just sort of tying my hands here a bit. And the detection procedure should produce some confidence estimate. Okay, it shouldn't be just 0, 1. Say, okay, with this very high probability, the watermark is detected. Okay, and I'm going to talk about something about a result that came from Bose. By the way, one thing that I'm as guilty of as everybody is whenever, since I'm getting old, whenever I see a paper, I always remember the senior author. So, I say Bose-Barak's paper, but it's really not Bose-Barak's paper. It's, as we know, all students do the work. It came out of Bose-Barak's group. And we'll talk about that. There is an impossibility result that if you don't put any limits on the adversary, they can do whatever, then it looks like it's impossible to have a watermarking scheme. So what we're going to say is we are going to be robust to very small perturbations by the attacker. And by the way, you'll see there was this watermarking scheme from Google, and they kind of finessed this by saying, oh, we are robust against all reasonable attackers. Okay, because I think you'll see later, I don't think we can be robust against sort of a powerful adversary. Okay, so I'll talk about the first scheme that came out. This is Kirshenbaum et al. Um, and Tom Goldstein and Jonathan Katz were the senior authors on it. And crypto folks should think about this as max. Since this scheme, there are a lot of schemes like this. There's a scheme from Stanford, uh, Percy Liang's group, and Scott Aronson has a scheme which he has been giving talks about from OpenAI, but I don't know why he has not published this. But he has given enough talks about that. Everybody knows what the scheme is. So I'm not going to talk about that. I'm going to talk about the first scheme by Kirshenbaum et al. And crypto folks should think about this as a Mac, basically. I think about this as sort of very similar to a message authentication code. And actually, it's a pretty simple scheme. Some language basics. So this is the sentence, and this is your model. And essentially, you get, these are the next tokens, and you get the probabilities of this next token. And you will probably, if you do a greedy search, you will say it's couch. So you'd say Matt sat on the couch, okay? This is just the next token prediction. What these guys do is you take the last token and the token, all possible tokens, you hash them to red or green, and that gives you the color on the token, right? Red or green. And essentially, I'm going to pick tokens that are green, okay? So this was showing up okay last night. Okay. And now the thing, what you can do is, instead of using a hash function, I can just use a pseudo-random function keyed by something as well. And it gives you sort of at each stage, it divides the token into green and red. Okay, and I'm going to pick the red tokens. And then basically what they're relying on is, in natural distributions, you're roughly going to pick half green, 50% green, 50% red. But if something is watermarked, I'm picking more green. And that's what they're relying on to detect. Okay. And at least in the paper, they are saying that there's false negatives. If you pick a reasonable threshold, there is going to be almost none. And false positives, there's a probability of some token being on the green list is half. You can set the threshold that this is also quite small. I'm going to skip this a little bit because I'm going to get back to it. Um, anybody see a problem with this? So suppose I give you a prompt, complete this name, Barack. Okay. This, I mean, it cannot be Barack Tramer, Barack Pepper. No, probably not, right? So what happens with this is with low perplexity kind of outputs on prompts, this gives you some very bad results. Okay, look, if you don't care about utility, I have a very good LLM. You give me a prompt, I give you a random answer. So what they do is this I found the most clever in the paper, to be honest. The rest of the stuff is pretty straightforward. So what happens is, um, ah, oh, there's something going on with Nicolette's. Sorry. Okay. So this is the low perplexity text. So what you want to do is you want to have where if some token is going to be picked with very high probability, like Obama, you still want to have that Obama is picked. Okay. So what they do is what I call it a logit boost. So what they do is the green tokens in the logit are going to get a little boost of delta. So they're going to be more likely to be picked. But still, if there is something like Obama that has overwhelmingly very high probability, the boost is not going to sort of, you will still pick Obama. So what they do is that this boost is called delta in their paper. And essentially what you do is each green token is going to get a boost now of delta. Okay? And they claim, at least in the paper, I think Florian, you probably have played around with this. They get some pretty good results with even low perplexity outputs. Okay, so if as delta goes to infinity, you go back to the previous algorithm. Um, when the perplexity is pretty low, it's you sort of bias toward the green tokens. Otherwise, I think Scott Aronson has a very nice example of this. If I give you a prompt saying, give me the next 50 primes, there's nothing I can do to watermark that, really, right? Uh, and I'm going to try to spend, the detecting the watermark is not hard. It's basically just hypothesis testing. Like if I give you sort of a natural text, given, you would say half are red, half are green, roughly, right? But if it is watermark text, I have actually set so that it is mostly green. And that's what you realize on. And when you detect the text, you basically just count the fraction of the green tokens and you use hypothesis testing. In some sense, what you're doing is you do a null hypothesis test and you try to reject that. That's it. It's actually a pretty simple paper. I think it also, I don't know if somebody remembers, I think it did win the best paper award at NeurIPS, I think, or whichever it appeared. But the idea is very simple. At each stage, I have a secret key that decides when to give the tokens as red or green. For green tokens, I give a little bit of a logit boost, and then I go on. And notice that there is no training involved here, right? I'm not going to spend too much time because I want to go to the public key scheme. As you can see, as the number of tokens grows, the strength of the watermark increases. By the way, and by the way, the gamma is the parameter that is set for the hypothesis testing, and delta is the logit boost. And you can tune it. So for example, if gamma is very small and I give a very large delta, then essentially I'm focusing on everything being green, and it's not very good for low perplexity prompts. And it is pretty robust, but it is not useful. And as you go towards more realistic delta and gamma and delta, you can tune these things, but it gets less robust. I am going to skip some of them. So you can do little tricks where what you can do is you can have the green list depend on just not the last token, but the last edge tokens, for example, and so on and so forth. There are all these schemes described in the paper. By the way, since then, there were a lot of attacks on this. But what happens is the robustness suffers if you do that. Because remember, what happens is if I change one token, because it has effect on a lot of other downstream things. So it's less robust. Okay, I'm going to now switch to, let's say, so that essentially, uh, let me go back. Okay, so these are secret key schemes. So you have a secret key that embeds the watermark. There's a secret key that detects the watermark. This was the first one that we talked about, Kirschenbauer, but there are since quite a few of these. I don't know whether, I don't know, Florian or Nicola, you know, a lot of them have been attacked, and it's unclear how robust they are. So with some folks at Berkeley, we started saying that, you know, we know that in court of law, you need digital signatures. You need public verifiability. Can you have a publicly verified watermark? And I'm going to spend a little bit time on this. And crypto folks can think of this as an equivalent of a digital signature. So here is how the scheme will work. So this will get a little bit more technical, then we'll pop back up. You will need whatever parameters you need for digital signatures. Okay, you generate a secret key, you generate a signature, you verify a signature. So that's what the first one is. There are two other things called watermark, where given a secret key and a prompt, you give a set of watermark tokens. And then there is a detect, which is given a public key and a set of tokens. It says true, I detected the watermark, false, I didn't. Okay, is that clear? So we bootstrap off a digital signature. Okay, and here is how kind of the algorithm sort of works. We take a first set of messages. So imagine first 10 things in a response. We extract the bits out of it. You can just almost think of this as a bit encoding. We hash it, and then we sign it. And then you decompose a sign into a set of bits, and then embed it through some procedure, what is called rejection sampling. Okay, and we will get to that a little bit. So this is kind of the flowchart of the generation algorithm. Extract works very similar. You take the first few sort of tokens, you extract, you hash, and that is from the signature side, you extract, compose, and then you use the verification of the digital signature. And I think one of the things that by the way, this is not, I just want to kind of give credit here. We were very heavily influenced by this paper from Miranda Christ and Sam Gunn. It was in a secret key scheme, but to me, that paper doesn't get enough credit. They were one of the first ones that really tried to nail the definition down of a lot of these concepts. And we were really influenced by that. So I should have probably put that on the slide, but shout out to the paper by Christ and Gunn. So definitions-wise, we have delta completeness, which basically says if there's a sufficiently long text and it was generated by the watermarking scheme, the detection scheme should detect it with, except for negligible probability, right? Good. So this is basically, it should work. You know, if you watermark, you detect, it should work and you should be able to detect it. There's also called case soundness, which is like very close to forgery in digital signatures, which just says that if I give you a lot of watermark text, which you can generate, you go through OpenAI API and you generate 50 possible responses, you should not be able to forge a watermark set of tokens. Okay. Now I can tell you this, my sense is that this is where I think the big companies are much more scared of forgery, because they know, that it's probably not going to be robust to a lot of perturbations. But forgery is a big thing, right? I mean, imagine if I take some objectionable text and able to embed a watermark in it, make a lot of noise about it, saying, "Oh, look what GPT-4 is doing," and then maybe even do something legal. So forgery somehow, I think, before a lot of papers, people don't talk about that so much. So this is basically saying that given watermark text, the adversary cannot generate another watermark text, or the probability of generating a forgery is negligible. There is also something called distortion freeness, which actually first I saw in the paper, the watermarking scheme by Percy Liang, which basically says that, let's say I give you responses from an unwatermarked model, and I give you watermarks, sort of text from a watermark model, you should not be able to distinguish it given polytime. Okay, there shouldn't be enough. There shouldn't be distortion so much. Like you shouldn't be distorting the sort of this too much. Now, this I think first time I saw in Percy Liang's paper of this whole concept of distortion freeness. I think the algorithm of Kirschenbauer, and at least that's what the paper from Stanford says, and also even Scott Aronson's scheme is not distortion free. Okay. By the way, just and there is also called delta robustness, which says as long as there is a large enough segment that the adversary doesn't touch, we are able to detect. Okay. And we already talked about this a little bit, so I'm not going to talk about this too much. Now, this is the key money slide, as they say. And essentially, I'm going to tell you how I do it for 1 bit, and then you repeat and rinse, right? You generate the message, which is sampled directly from the model, compute the signature, sigma from a hash message. Now, basically what I do is, for each bit, I'll sample a token from the model, and I will hash that token and say, hey, did it match the bit of my signature? If it didn't, I will go back and resample. And this is where the rejection sampling comes in. And this is where we need a high enough entropy sort of thing so that we can use rejection sampling. And again, I think I already talked about the detection algorithm. And the detection algorithm is very symmetric. I don't want to, you just extract the signature, you extract the message, and you just check the verification goes on. There's not much interesting goes on. One of the most interesting things, and I should give credit, I can take credit for it, this is Sanjam Garg's idea, is that what happened is, if you in practice you're encountering a low entropy output, like the largest carnivore of the Cretaceous period was Tyrannosaurus. So, the only thing is Rex, right? Without using some error correcting code, the entropy we need to embed our watermark is pretty large. And with error correcting code, what happens is, essentially, we are able to embed watermarks in even sort of that entropy threshold over which we embed the watermark goes down. Okay. To me, this was kind of one of the cool. The rest was all very standard definitions. This to me was pretty interesting the way we do it. I'm not going to do it too much. Obviously, it's not a secret key scheme. It's a public key scheme. So we need larger number of tokens to embed our watermark. Um, and, I think Jaden produced this for me from Mistral. We produce good outputs. It's not producing junk. The watermarked outputs are not junk. And, by the way, one thing that Jaden, who's a student of Sanjam Gers at Berkeley, did is that the Christ et al. Paper, which we, as I told you, we heavily base on, they are theoreticians. The only thing they code is in LaTeX. So he actually actually I was talking to a theory person. He said, oh, I code, I write a lot of LaTeX macros. So that's what they're mostly from the theory crowd. He'd actually implemented the whole scheme so that we could compare. And essentially the takeaway here is that we are not generating junk. We are generating high quality outputs. And then he also, this basically says that the score as given by GPT, how good our outputs are, is pretty good. Now, let us get into attacks a little bit. There's always a lag on these things. Yeah. So this is the first attack that a lot of people tried, and it kind of worked. And it actually works remarkably well. Why is there this watermark on the back? What's going on? It's not on here. Okay. So I say it's very very simple. You take a bunch of watermarked images, bunch of unwatermarked images, train a binary classifier to classify something is watermarked or not. Then you basically, if you have to remove the watermark, you run the PGD attack on this classifier. That's it. And I would not name the company. Somebody told me that this kind of worked a lot of the watermarks that they had inside the company. And that's it. This old adversarial PGD attack coming back to attack the watermarks. Now this, okay, I think this is weird. That's not me, by the way. There's something going on. I think spoofing attack this is from Sohail Faizi, which to me is the most interesting. As I told you, this is basically what it does. It takes an image of random noise, it injects the watermark in it, and then takes the unwatermarked images and sort of does some addition, and it's detected as watermark. Okay, so this is able to inject the watermark in an unwatermarked text. And to me, I suspect they haven't stayed out and said it, but the companies are most worried about this. That I can take some objectionable image and say it came from GPT-4. One very simple thing you can do is take a text, use one of the paraphrasers to paraphrase it, keep recursively doing it until the watermark goes away. Okay? This almost breaks a lot of the stuff. So all this is going towards is these things don't seem very robust to, oh, by the way, these attacks also worked for those zero-shot GPT and so on and so forth that was going on. They don't seem very robust to an active adversary. So I want to keep filing that these attacks are pretty devastating. So by the way, one thing, my pet peeve is somebody who's not from the security crypto community, they always say, oh, but everybody's not Nicholas Carlini or has a PhD from Berkeley. So, this is resistant to reasonable attackers. And I kind of reject that. I think we were also we had broken a paper called InstaHide earlier, and the authors of that paper also made the same argument. I don't agree with this. There's a tragedy of commons in security and cryptography where one smart person has to really figure out But then I can read Nicholas Carlini's paper and implement it. I don't need to be as smart as him. Or, I mean, God forbid, somebody's actually people put on GitHub code. But I've seen this argument being repeated a lot, saying, oh, this is not like everybody doesn't have a PhD from Berkeley, MIT, and Stanford and CMU. So, what the heck, you guys are just, but I actually don't like that argument at all. Okay, so this basically is a paper that I really like. It's still on one of the best venues in CS called Archive. I don't know why they haven't, I don't know whether they have published it or not. Maybe they have, but this is, and what basically this says is, to me, the takeaway here is, if you don't put any restriction on the adversary that how much they can change or edit distance, probably a resistant, robust watermark is not possible. Okay? So I like the name, Watermarks in the Sand. And here's the algorithm. The algorithm is very simple. And analysis is hard, but it's actually not that hard either. So here's how the algorithm works. It's pretty simple enough that I can cover it in 2 minutes. So you have a prompt X, you send it to GPT. I don't know why I keep using GPT, just because, but Claude, Gemini, whatever you want. You get a watermark response. You assume there is a quality oracle, Q, which can be another LLM, maybe a weaker one if you want, Mistral or something like that, which says how good your output is. You have a perturbation oracle that perturbs the output. So you can think of this as a paraphraser, if you will. And there is a random walk length T. So the algorithm is dead simple. You get the initial response here from your model. Then you repeat this capital T times. You perturb the sort of the output of the model. And if the quality oracle doesn't go down, the quality of the response doesn't go down, you keep it and you just keep going. That's it. That's the algorithm. Now, the theoretical result here is very interesting. So you can imagine that these perturbations are creating kind of a graph over the responses, right? And the idea is that if this is a random step, then you're taking a random walk on all the possible responses for that prompt. And the idea is, and then they put some rapidly mixing stuff in there, but it's essentially saying that if there is enough high quality responses, you will find it with a capital T. That's about it. And they actually broke most of the watermarks using the scheme. And so this algorithm is pretty devastating to me. It basically is saying that, but notice that the perturbation can really change. You will change the entire output at some point. So you're not bounding the distance. So this basically is essentially saying that if I don't put any limitations on the adversary, then probably a robust watermark is not possible. I'm saying probably because there were some, as good discussions happen on Twitter, some people were discussing it, but I think this is a pretty devastating attack. Any questions so far? So where are we? There are a lot of secret key schemes. There is a public key scheme that we have. The Gen AI laws are all talking about watermarking, but mostly saying thou shalt watermark. So where do we go from here? How much time do I have, Nicola? It's 10 minutes, okay. And here I would like to open up the floor a little bit. As we saw just from that paper, Watermarks in the Sand, probably it's not possible to have a model that is robust to all adversaries. You will have to limit somehow the edit distance or limit the adversary. So some use cases are still okay, like filtering, right? A lot of times what happens is, I think, Nicola, you had a paper on it. If you generate things using GPT-4, you put it on your website, that it slurps it again to train. that can actually create some model collapse. So the OpenAI uses it to filter the stuff that they created. Okay, so that probably use case is okay. I mean, if I'm going to write my bio using GPT, I mean, I don't have that much incentive to remove the watermark that GPT put. I mean, yeah. So the second one, but if there is an active adversary, even with students, like there are some universities, they're saying, oh, we will find if some of your essay was written by GPT. I mean, students are pretty clever. I think they have the incentive to you to not catch it. I think how many of you know of that tool called Moss? Remember that Alex Aiken and these guys had which find these code that you're plagiarizing, and the students got eventually pretty good at getting over that tool. So that I don't know what happened to that sort of company. And so the thing is, there has to be and I don't know. There has to be some use cases where there's a disincentive to remove the watermark. So, for example, I think my best example, I think it was one of in Scott Aronson's talk was, I can buy a painting by a famous painter and scratch the signature off, but I'm hurting myself, right? It has to be some use case like that where there's a disincentive to remove the watermark. So, for example, just like Florian and Nicola, I spent some percentage of time at Google, and there is some talk that if you're using generative AI to generate a content, and they're not able to detect it came from Gemini, whatever, GPT or Claude or whatever, then they'll say, you go back in the review queue. We have to do a bigger review for you. Okay? We have to go over everything that you did and so on and so forth. Very similar to Apple and so on. What they do is if your code is really obfuscated for an app, they can go back to you saying, no, Florian, your app, we can't do the analysis. So you obfuscated it too much. We need the full code, otherwise you're not getting onto the App Store. Okay, so something like that where we somehow use policy, disincentive, all that to sort of otherwise I don't think we will ever have a watermarking scheme that is robust to all that. Yes, Florian. Yeah, and actually that exactly comes in Android and Apple iStore as well, where they say these review processes for developers and all that is disadvantaging small players. Yeah, I agree. So that's why I kind of put it towards the end. It's an open sort of question, but I think in Google they're talking about this, that like if you are not using one of the reputable sort of, so to speak, LLMs, whatever you want to call them, reputable, then we will put you back in the review queue and do a bigger review of you. But as Florian said, there are some fairness issues there as well, right? If you're from a small country, there's not big ecosystem there or something like that. But holding my cynical hat on, I think they're much more worried about forgery. Okay, and if you meet me over coffee, I can show you some stuff. Is that imagine what I can do is I create a bad article about myself saying, oh, Somesh is stupid, his IQ is 0, he's ugly as well, and so is his kids or whatever. And then embed a watermark from it, forgery, saying this came from GPT-4. I go all over Twitter and say, look, what the heck is GPT-4 saying about me? And I mean, it's first of all really bad for their brand, probably. And the second thing is, probably can at least drag them into a lawsuit and settle out of court, right? I think I think to me, they are very worried about this, to be honest, because I think they probably know that it's not, getting a scheme that is robust to a sort of a full adversary is probably not that easy. And I think this is a achievable goal. Okay. So, by the way, one thing with watermarking, which is really scary, is that we are having all this discussion, all these attacks, what's good for, but the laws are just going forward. It's like I mean, so I don't know what to do about this. Um, it's coming. I mean, they will have to watermark, even if it is some junk watermark, because the law said it. Which is, I don't know whether we want to be there. We want to do that. So it gives me that, but as I also said, given the attack landscape, and especially this result from, again, I only remember Bose-Barak's group, uh, is unclear what are the use cases where this works, and what should those use cases be. And I know several people in this audience are interested in that subject. And maybe, as I said, the best solution might be a combination of end-to-end system or sort of a policy solution. And I think one thing that I do want to say is that a couple of the meetings that I have been in from the government side is it's very disconcerting that it's like that elephant in the room, right? From different things, you look different. What they think is watermarking, some of the policy people and some of the legal folks is just not what we can do. They think it's solved. Oh, look at this paper from folks from Maryland and Stanford. Oh, it's done. It's over. So because they don't track everything like attacks and all that like people here, so they don't know the limitations, although it's coming. So I think there is a lot of benefit from everybody should be getting involved in this discussion. Otherwise, it's basically a law without any teeth. They say, oh, you have to watermark. Well, I'll just put something in there. It might be totally not robust. So I think there is more academics should be getting involved here. Otherwise, I think it will just be a toothless law.